All right, everybody. So today what we're going to do is we're going to look at how you can use binary numbers to represent things other than just decimal numbers. Now, we've already looked at how I can take a decimal number and convert it into a binary number. So, we can say like, oh, we've looked at how to do that, and we've looked how to go both ways. And so today what we're going to do is look at how do we get this number to start with? How do I turn music into numbers? All right? Or how do I change a picture, good pictures and bad pictures, into numbers? All right? So how do we actually go about doing that? So today we're going to look at three things. We're going to look at music, we're going to look at text, and we're going to look at graphics files or pictures. So we're going to start with the most straightforward one. The most straightforward one is text. Now, let's say I had an image of some text here. Now, each of these spots is called a character. So an H is a character, an I is a character, a comma is a character, the space is a character, the M, the O, the M. It's all characters. And we'll look at it, and we add it up, and we have 7 characters. Okay? So how do I convert that into numbers so that I can save it on a computer? Well, basically just like you probably did when you were a little kid and you had like those little codes and A was 1 and B was 2, we have a similar thing, except we call this ASCII. Now, ASCII stands for the American Standard Code of Information Interchange. I know that's a mouthful. But basically, what it does is it tells us what letters and what symbols represent what things. So if you would go and if you wanted to see the actual ASCII table, you could look it up and say, just Google ASCII table, and you would find a table, and it would give you all sorts of symbols, and it would tell you what corresponding letter they went with. So for example, if I wanted a capital H, and remember a capital H is a different symbol, so it's going to have a different number than a lowercase h. So a capital H is 72, and a lowercase I is going to be 105. All right, so we will have all of these, and if I want things like a comma, they have symbols too. So a comma is actually 44. A space is 32. And an M, lowercase m, is 109. Lowercase o is 111. And a lowercase m, like we said, is 109. So I have these numbers. And what I could do is convert them into binary. So I'd convert this exactly. I don't actually know those are the binary numbers. But what I'd do is I'd convert those into a binary signal. Now here's the problem. To make it real obvious, let's simplify this, okay? So let's say this is 5, and this is 3, and that's 7, and this is 8, and that's 4, and 1, and 4. So I convert 5, 1, 0, 1. I convert 3, which is 1, 1. I convert 7, which is 1, 1, 1. I convert 8, which is 1, 0, 0, 0. 4 is 1, 0, 0. 1 is just 1, and 4 is 1, 0, 0. Now, a computer doesn't pause in between the signals because you can't tell the difference between a pause and a 0. A 0 is no voltage. A pause would also be no voltage. So when a computer records this, what it's going to do is they're all going to get mushed together. You're going to get 1, 0, 1 from here, then 1, 1, then 1, 1, 1, then 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0. Now, where are the breaks? How do I know how to break this up? Maybe it's this. That's a 2. And then I have 7. And then I have another 7. And then this is another 2. And 0, 0, 0, 1 is just 1. And maybe that's 3. And then this is 0. Like, how do I know how to break it up? This clearly is not right. I could break this up a ton of different ways. Instead of breaking it up like that, maybe I break it up like this. I say 1, 1, 0, 1, 1. All right. This is 11. And then maybe I get 1, 1, 1, 1. And that's 15. And then I get 1, 0, 0, 0. And you can see, depending how I break it up, it's not going to work. So the key here is what you do is you make every symbol the same length. So if we make them all 8 characters long, instead of this being just 1, 0, 1, what I do is I say 0, 0, 0, 0, 0, 1, 0, 1. All right, so this is 8 bits. The next one is, and that's 8 bits. And like any number in decimal, if I have 47, I can put zeros in front of it, and that's still 47, that's still 47, that's still 47. These zeros in the front don't matter. So what we do is we pad the numbers if we need to make them all the same length, so that way we know every byte, every 8 bits, we break it, and this is one letter, and this is the next letter, 8 of them. That's the next one, etc. So that's how we take text and break it down. Now remember, it's not 5 and 3, it's, 111 and 42 and spaces 32 and all that. But the idea is the same, it's just these numbers be a little bit longer. And that's how we break down text. Now, let's look at how we break down, say, sound. So, sound is a wave. So if we have a wave, what we do is we use a process called sampling of the wave. And we have a certain number of finite levels. So we'll say this is 0, 1, 2, 3, 4, 5, 6, 7, 8. And every so often we sample the wave. Now, for most music, this happens 44,100 times a second, which is a lot. So, after 1/44,100th of a second, we sample the wave here, and we round to the nearest number. So we say this first number is 5, and then we sample it again. And we'll say, okay, that's 7, and we sample it again, that's 8, we sample it again, we'll round to the nearest number, 7, sample it again, maybe 5, and so forth. And what we do is we'll take these individual numbers and we're going to turn them into binary and save them. So 1, 0, 1, 7 is 1, 1, 1, 8 is 1, 0, 0, 0. And you see we have the same problem that they're different lengths. So what we do is we use the same process, and we say how many digits are we going to make each number, and we make them all the same length. And that way, when we save them, maybe we're going to make them all 4 digits long. So the 5 becomes 0, 1, 0, 1. The 7 becomes 0, 1, 1, 1. The 8 is already 4 digits long, 1, 0, 0, 0. And we know that when we go to break it up, that's our first one, is 4 digits. That's 4 digits. That's 4 digits. All right. This length of the number here, in this particular case, is called the bit depth. So for this one, the bit depth equals 4. For the last one we looked at with the text, the bit depth equals 8. And bit depth of 8 is pretty standard for text because each character then ends up being 1 byte. And that's how the ASCII table is set up. Music can go a couple of different ways. Bit depths usually are either 12 or 16 or 24 for music. Obviously a lot longer, and that's because when you're making actual recordings, you want to have a lot more levels in here to give you a more accurate representation of what the music actually sounded like when it was recorded. So that's how you would record music. If I wanted to think about how music, how I recreate the music, basically what you do is you would take the string of numbers that you get. So let's say 1, 0, and if I knew this was a bit depth of 4, I would take this 4, that 4, that 4, and that 4. I'd have my binary number here, and then I'd break it down into a decimal number. So that's 8, 7, 5, 8. And then when I went to create it, I would make my first point at 8, next point's at 7, next point's at 5, next point's at 8, and then it just kind of recreates the curve of the music from those samples, and so on. All right. The last one we're going to look at is how you can digitalize image files. So when you see an image file, say we've got an image here. We've got some blue sky things going on. We've got like a tree. This is lovely. What the computer does is it actually breaks the image down into its individual pixels. So it looks at the very first pixel, and it gives it 3 numbers. So it measures this pixel, and it says how much red is on it on a scale of 0 to 255. And the reason it's 255 is that is 1, 1, 1, 1, 1, 1, 1, 1. That's the biggest 8-digit number we can make in binary. How much red is in it, how much green is in it, and how much blue is in it. All of them on a scale from 0 to 255. And it converts that to binary. Now this one's mostly blue, so maybe it would have red of like 15, green of 40, and blue of like 200. We'd convert all of those numbers into binary and save them. Then it just goes and does the next pixel. And this is why image files can be so large. It's not uncommon for image files to be 10 or 20 megabytes, which if you think about it, 20 megabytes means 20 million bytes, which is 160 million ones and zeros for one high definition image, because you're looking at all of these individual pixels. To take this a step further, if you want to think about video, all video is a whole lot of pictures, usually 24 or 30 of them per second, and the sound files that go along with them. And we know how to record pictures, and we know how to record sound now. So between those two, you combine them together and you can record video. So that's how you can take file formats that you wouldn't think of being able to convert into binary code, like text, like pictures, video, and sound, and how you can actually convert them first into decimal numbers, and then all decimal numbers can be converted into binary numbers. So that's how that works.